Distinguished speaker of this afternoon, Dr. ADITI SEN, respected principals of JNV Chitradurga, Mangalore and North Sikkim, respected viewers, very good afternoon to everyone. We are very proud to have Dr. ADITI SEN as a resource person for today's session to speak on the topic quantum technologies under Vigyan Jyoti program. This program is jointly hosted by JNVs of Bangalore Urban, Chitradurga, Mangalore and North Sikkim. As a matter of fact, Dr. ADITI SEN is an Indian scientist who has won many awards in the fields of science, and one among is the prestigious Shanti Swarup Bhatnagar Prize, one of the highest Indian science awards in the year 2018. And she is the first women recipient of this prize in the physical science category. Now, I would like to request Sri Srinivasan, Principal JNV Mangalore, to welcome Madam to this program. Sir, please.
Yeah. So, good afternoon, ma'am, and good afternoon, my fellow principals of Navodaya Vidyalaya, Mr. Ashokan, my dear students of Vigyan Jyoti program as well as Navodaya Vidyalayas. A very good afternoon to everybody. I'm extremely privileged and happy to introduce Dr. ADITI SEN. As Mr. Ashokan told, she is an Indian scientist and associate professor in Quantum Information and Computation Group at the Harish Chandra Research Institute, Allahabad. And she is known for her research on quantum information and computation, quantum communication, quantum cryptography, and many body physics. The CSIR, the apex agency of the Government of India for scientific research, awarded her the Shanti Swarup Bhatnagar Prize for Science and Technology for her contributions to physical sciences in the year 2018. And she happens to be the first female physicist to be given this honor. In 2012, she also won the Biennial Booty Foundation Award given by the Indian Physics Association to young scientists who have made outstanding contributions in the area of theoretical physics, astrophysics or biophysics. She has also been a recipient of the prestigious Ramon E. Cajal, a fellowship in Spain, and the Humboldt Research Fellowship given by the Alexander von Humboldt Foundation in Germany. She has around 30 international papers to her credit and celebrated personality. We are very, very happy to have Dr. ADITI SEN to address the Vigyan Jyoti children and Navodaya children and staff. I'm extremely delighted to have you, ma'am. Over to ADITI, ma'am, with a lot of a cartload of welcome and greetings to you, ma'am. Over to you.
Okay, thank you very much, and it's really a nice opportunity to speak with school children. As you know, I am associated with the Research Institute, and so we had some outreach programs, so where we want to tell students in a simple way the physics and mathematics. So I really, when I got these invitations, I was really happy that I will get an opportunity to speak with students in schools and try to tell that what are the research areas that I actually work on, and it's really challenging to tell what we are working here, and so I always really feel, I mean, this has also, I have some interest to tell in simple language the research area that we are doing here. So maybe now I shared the screen.
Yeah, yes, madam. Please.
Yeah, so can you see my screen?
Yeah, it's visible, madam.
Okay.
It's visible.
Okay, thank you. Okay, so I will be talking about technologies, and as at least has been mentioned already, that I work on quantum technologies. Okay, so there is something that I cannot change my, yeah, it's now good. Okay. Okay, so I work on quantum technologies. I will tell you in details in next 1 hour what do I mean by quantum technologies. So technologies can, I mean, in our daily life, there are several technologies that we use every day. And in this COVID situation, probably even in this educational purpose, there are two things which play an important role in computer, which help us to do several tasks which we require in our daily life. Another is the communication devices, which help us to connect with our friends, relatives, and in schools, colleges, etc. And even today, we are, I mean, I'm speaking over Zoom, so we understand the importance of communication devices. Now, communication devices can also broadly classified into two categories. One is communication without security. That means where we want to transfer certain information, but we don't care about whether it is known to other person, third person or not. So that is what I mean by communication without security. And there are another kind of communication technology that we use every day is a secure communication. That means where the information is locked somewhere, and a few people whom we want to share this information has a key, and by that key they can open the lock and can share the information. So this is the basic principle of secure communication, or in other words, it's called also the cryptography. Now, I will, as I have told you, I will try to convince now next 45 minutes or 1 hour that if we build quantum version of these technologies, then this will actually enhance the capacity of sending information, or capacity which we, from the perspective of computational tasks that we can do in our computers. So this is the main aim of my research, and I am going to tell you why the quantum versions are more efficient than the technologies that we are using nowadays. Now let's start with the computer part. So as I said, that the computers are like desktop, laptop, even the much bigger or much powerful computer like supercomputer, or the cluster computer that usually people use in for heavy computation. These computers I call the classical computer, because the basic principles on which these computers are working are based on the classical concept, either classical information theory, electromagnetic theory, and so on. So these machines I call the classical computer. Okay, so human beings are using, here I show a funny picture where we see that even the cats looking at some Tom and Jerry cartoon through a classical computer, through a laptop. Now, classical computers, or the computers that we use nowadays, are useful from different fields. For example, as I said, that in this COVID situations, we understand that in educational field, these computers are very important to store data in hospitals or in medical science stream. Also nowadays computers are useful in banking, in government offices, in marketing purpose. So there are a lot of areas in which computers are useful. So what we actually do in this, by using these computers, we can write documents, we can use internet for example, to send emails, or to internet. By using internet, we can also gather informations about certain subjects. And for example, this lecture is streaming, and you can listen this lecture by using your computer. So there are several purposes in our daily life where the computers are really essential. Now, there are other issues also which we can do via computer. For example, we can do certain mathematical calculations by using computer. So what do I mean by mathematical calculations? For example, we can say we have a function, we want to draw it, we can use computer. we want to say, for example, we want to write an algorithm by any language that we know, and we can try to solve certain mathematical problems. It can be simple or it can be difficult, but people can try to write certain, say, for example, I talk about function plotting, but you can suppose you want to solve polynomial equation, and you can write a program how to solve the polynomial equations by using a computer. So before I talk about some mathematical problem that classical computer can solve, I will talk about few specific problems. Before that, let's talk that what are the basic unit that classical computer uses. So the basic unit that classical computer uses bit. That is one of zeros or one. So any input that I give in a classical computer can be written in terms of zeros and ones. Then there are some logic gates that classical computers perform that we learn even nowadays in school, and we get certain output again in bits, that means again in zeros and ones. So this is the basic principle that classical computers follow. Now let's talk about certain problem which we can solve by using classical computer. Say, for example, we can try to solve the problem where I give you a number. You have to tell me whether the number is prime or not. So this is, we can tell that this is a prime identification problem. Now, up to 100, even in our primary school, we learned that what are the prime numbers if we consider from 1 to 100. And here I mark it with circles, which are the prime numbers. Now, if I go up to 1000, you can also count prime numbers. So this is a table of prime numbers up to 1000. So here we talk about a 3-digit number. So as we know that the prime number has a property that it has factors 1 or itself. So you can write it down, a program which can tell me whether a number is prime or not. Yes. Any questions? Okay, so now let us consider that, okay, up to now I talk about a 3-digit number. Let's consider that I give you a 10-digit number. Okay, so here I put a 10-digit number where the last digit is a odd number. So as you know that if it is an even number, then I can always tell that this has a factor 2. So it's not a prime number. So here I I actually typed this number randomly, and I was only careful that the large digit is odd. And now if I ask you to find out whether this number is prime or not, you have to be more careful, because you have to write a program which can check in a reasonable time whether this number is prime or not. Actually, this is not a prime number because it is divisible by 7. Now the question that we ask, instead of 10-digit number, suppose I give you a 50-digit number or a 100-digit number, and I want to ask you the same questions, whether the number is prime or not. So you have to write a program by which you will be able to identify whether a number is prime or not. So if I ask a general question that can you design a program which can tell me at the end of the day whether a number is a prime or not, and the number that I will give you a n-digit number, so an arbitrary digit, it can be 100, it can be 200-digit number, and so on. Now this problem looks so simple, but it was not known whether such a program can be written even in our normal computer or not till 2002, where this 3 people from IIT Kanpur has solved this problem. They show that they proposed an algorithm where they show that any given number, they can check whether this number is prime or composite within a polynomial time. That means within a time which is reasonable, you can say, if you don't want to go in a more technical term. So more reasonable time, like if I give you a number within say a day or two or a week, I will get the answer. Now these are the three people who solved this. So this is a nice scenario where we know that prime identification problem can be solved in our normal computer, say desktop, laptop. Actually the program, you can find it in the, if you Google it, then you can find it, the program. It's very small program and it can solve this problem. Now, if I talk about another problem, another mathematical problem, the second one. So this I call the prime factorization problem. So here the task is the following. I will give you an integer. You have to tell me whether the integer, what are the prime factors it has. So what are the prime factors? Give me this integer. Now, for example, if I give you a number, say 45. Hello? 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 Hello, can you hear me?
Yeah, we can hear you, ma'am. We can hear you.
Okay, okay. I thought that the connection was lost.
No, no, no.
Okay.
Oh, very much okay.
Okay, thank you, thank you.
Yeah.
Sorry. Okay, so if I give you an integer, say 45, then you know that the prime factors is 5 and 9. So it's actually 5 and 2 3s. So 3 and 5 are the prime factors of this number. Integer, and I want to write down a program so that I will get the prime factors of all of the integers. Now, for example, in this case, this 8-digit number, you can try to find out the prime factors and you will get that this is the prime factors. So, as I said, that if I make 8 digits to 80 digits or 100 digits, then whether we will be able to design a computer program or able to design a program which can be solved in a reasonable time by using even a very powerful computer which are available in the world. 9 digits. And it has been station.
सुरू झाले आदिती संधी बरं बंद कर बरं आवाज येतोय 18 पार्टिसिपेंट साथ आहेत
Oh. There is no classical algorithm available by which one can solve this problem efficiently. So in other words, I have an n-digit number that is an arbitrary digit number. And if I want to solve by using a powerful computer, powerful classical computer, then it will take almost technically exponentially n steps. So in other words, it's not possible. This problem cannot be solved by using classical computer in a reasonable time. So there is till date no efficient classical algorithm available which can solve this prime factorization problem. Now in 1994, Peter showed that if we use quantum mechanics, then this problem can be solved efficiently. That means this problem can be solved in a reasonable time. And technically speaking, this problem can be solved in polynomial time. So we can reach, or we can do it by using quantum mechanics. This problem can be solved more efficiently by using quantum mechanics than its classical counterpart. So this is Peter Shor, US mathematician, and he actually solved this problem, and it really showed the quantum supremacy. That is, quantum computer will be very powerful compared to the known classical computers. There are many algorithms over the times developed, like there are Grover's algorithm, Deutsch-Schultz algorithm. In all these algorithms, it was shown that the quantum mechanics helps to reduce steps, or the efficiencies of these algorithms can be enhanced, or the task can be better, task can be performed in a better way by using quantum mechanics. Now, since I'm talking about quantum mechanics, so I briefly tell you something which are, I mean, quantum mechanics is a vast subject, but I will tell you some interesting property which actually help to show, or to which help us to understand why quantum computer is better than the classical computer. So the quantum mechanics, quantum physics describe so if I talk about the Newtonian mechanics, so the classical mechanics or the electromagnetic theory, this theory describes the motion of a macroscopic particles. On the other hand, quantum physics describes the situations of the particles where the particles are microscopic. That means they are either atomic or subatomic. Now it was around 1900 it started formulated, and the quantum mechanics that nowadays we learn or we study in colleges and universities, or in higher studies, are mainly formulated around 1920s by several renowned scientists. For example, Einstein, Schrödinger, Heisenberg, Dirac, Indian physicists like Satyendranath Bose, C.V. Raman, etc. Now this et al. Which I put is extremely important because there are many important scientists here which I haven't mentioned, including all experimentalists. They play an important role to build the quantum mechanics or the modern quantum physics. Now this is probably many of you have seen this picture. This is probably one of the famous conference, Solvay conference in 1927 in Brussels, where most of the famous quantum physicists were present, who actually helped to formulate the quantum mechanics. You can also see women, among all these women physicists, Marie Curie is sitting here. So I just, I mean, as I said, I don't want to go into detail in mathematical the formalisms of quantum mechanics, just to tell you briefly that any situations in quantum mechanics, any situations, to describe any situation in a physical system, we actually use something called vectors. And these vectors is defined in a linear space where angle is defined. So, and this, when a space, linear space has an angle, that's called Hilbert space. And we talk about this two-dimensional Hilbert space, and they represent, for example, the spin of an electron. As I said, that quantum mechanics describes microscopic particles like atoms, photons, electron, proton, neutron, everything. So if I want to describe the spin of an electron, then I use this two-dimensional Hilbert space, which is where these are complex Hilbert space. We don't want to go into detail, and you don't also have to, this is just for completeness, I put this slide. So just to compare that, as I told you, that compare between, let's compare between the units which we use in classical computer and the quantum computer. So in a classical computer, the basic unit is bit, as I have told you, that is, it's between zeros and one. In quantum computer, the basic unit is qubit. So this is quantum bit. What is quantum bit? It's actually a two-dimensional quantum state. Now, okay, since I haven't told you what is quantum state, just to give you an analogy. So if you have a sphere, like a ball, then if you consider the points on the surface of the sphere, these all points actually describe this qubit. So there are infinite number of points in the surface of the sphere, in the surface of the ball, and this actually describes, if I want to describe it in quantum mechanics, they are the two-dimensional quantum states, and they are the qubits. Now, there is another important thing that plays an important role to build quantum computer or any quantum technology is the superposition principle. So what is that? In nature, we see there is a cat which is alive, or we see that the cat is dead. But quantum mechanics tells us that there can be a quantum state which can be consider a situation which can be tell us that this state is in alive plus dead. So that means there will be a scenario where something like that, the superimpose the picture that I am showing. So there exists in quantum mechanics, there exist states which can be alive or which can be dead, but at the same time there can be a state which is alive plus dead. And this we cannot see in classical world or classical concepts, classical mechanics, or in electromagnetic theory. Now, this is actually the success of Schrod's algorithm, the superposition principle. So just to stress that the success of this prime factorization or the prime factorization problem can be solved by using quantum mechanics is due to the fact that there is a superposition principle in quantum physics. Now the next question, okay, up to now, whatever I have told you is mainly the theoretical work. The Peter Shor has shown theoretically that quantum computer can be powerful. It can solve certain problem which cannot be solved till date by using classical computer. Whatever, I mean, classical computer can be as powerful as possible. Even then you cannot solve it. Now this is, whether this is just a theoretical prediction, it is no, it is not. It has been shown that you can actually build quantum computer in laboratories. So this is European Union has published a timeline of quantum technologies they are planning to build in over next 15 years. And you see that they expect to build a proper quantum computer by 2035. But in between, they are planning to build several quantum technologies. There are several companies who have built a small scale quantum computer, like Google, IBM, Microsoft, Intel, and even the startup companies are trying to build certain small quantum computer. For example, there is a quantum computer IBM has built, which is 20 qubit chip. So here, as I said, quantum computer has a basic unit, which is qubit. And so by 20 qubit, they build a quantum computer. So till today, there is a 72 qubit quantum computer, which has been built by Google. And if you are interested, you can look at several websites. You can Google it and can find all this information. But here I want to stress that if you really want to build a computer by using quantum mechanics, which outperforms classical computer, then we have to build a computer which is consisting of around or more than 1,000 qubits. So in some sense, this small scale quantum computer can demonstrate certain issues, certain problem they can address, but the prime factorization problem that I have told you, just to show that it can be better than the classical computer, then we need to build a quantum computer which is built by using, say, 1,000 or more than 1,000 qubits. Now here I just want to stress one thing, that if we build a lantern, or if we build a very good, say, candle, now this making a very good or powerful lantern or candle doesn't lead to a electric bulb or LED bulb. This technology is completely different than the technology that we use to build a electric bulb or LED bulb. So this is a technological revolution gives us this electric bulb. Similarly, making a very powerful classical computer doesn't lead to quantum. Even if you just, we know that a few years back, the computer that we had is not as powerful as today's computer. So we understand that classical computers technology is also improving, is developing. But to make a very powerful classical computer, that doesn't lead to a quantum computer. It has to be built from a different, using a different principle, using a different, this is quantum physics. Now I move to the another part, which is a communication devices. So as I said that communication devices can be two types. One is without security, another is secure communication. So let's start with without security part. So, okay, as I said, I mean, this audience probably are all convinced that communication devices are very useful. And probably we all understand in this critical situation that communication devices really help us to connect each other efficiently. We know that in old time, there are different way people use communications, for example, pigeons. Some years back, at least in my time when I was small or I was kid, we used to get informations only by reading newspaper. And now probably my kid actually getting informations, most of the informations via internet. So there is also a kind of technological jump that we see. So this you can see that probably the old machines and now people use different machines. We use notebook to write our notes. Now people use iPad or mobile, or they record it in mobile. Or in laptop, their lectures. So to tell you about communication, so any communication device involve at least two parties. One I call Alice, another is Bob. Now Alice and Bob are situated in two distant locations where there is a distance. Say for example, Alice is in Bangalore and Bob is in Allahabad. So they are now not close by where they can just talk each other. So they have to build a device to communicate. So I call Alice to be a sender and Bob to be a receiver. This can be Alia or Barun. So as I said, in old time, you can think about two kings are sending information from one kingdom to another. There are nowadays via mobile phone or land phone, you can connect. So in this communication process, always sender wants to send some information from her place to the receiver's place. Now, how you actually, how the communication protocol are built. So usually Alice encodes certain information. Suppose Alice wants to send that something like Hyderabad. So what Alice can do? So Alice can send Hyderabad as it is, or Alice can, instead of sending Hyderabad, Alice can send this. Now this is not a random alphabet. You look, I made it that H is now encoded as K. So it's a 3-step in our 3-step forward in alphabet. So Alice encodes these informations in this alphabets. Alice sends nowadays via optical fiber. Previously by some horse rider, maybe getting these informations and going to the receiver. And now Bob, the receiver, gets the information and decodes this information. So if it is written Hyderabad as it is, then immediately he gets the information. If it is written like that, then Bob has to decode it and gets the information that Alice wants to send. So there are kind of 3 processes or 3 steps that one has to follow if we talk about any communication protocol. One is encoding, another is sending, and third is a decoding. Now, since we are talking about quantum technologies, now this information sending that Alice wants to send some information to Bob can be of 2 types. Either Alice wants to send some classical informations, which are means that anything, as I said, that informations can be transferred to bits, or it can be a quantum information. That means it can be certain quantum state that Alice wants to send to Bob. This quantum state can be qubit that I have already talked about. So let's talk about certain thing which we call quantum state transfer. So this is another quantum communication or communication technology that the classical concepts cannot give that efficiency, as I will describe, and it will be clearer when I go to the end. And this protocol is known as quantum teleportation. It was discovered in 1993 by 6 scientists. Now, as I said, the task is to send an arbitrary quantum state, that is an arbitrary qubit, from sender to a receiver. Now, as I said, that the qubit, you can think of an arbitrary point in a sphere. Now, to describe an arbitrary point in a sphere, because surface of the sphere has infinite number of points. So to describe these arbitrary points in the sphere, you actually need infinite number of bits. That means by using classical computer, we actually need infinite amount of classical communication to send an arbitrary qubit from Alice to Bob. Now the question is, what about quantum device? Whether we get certain advantage, whether the efficiencies will be enhanced or increased. Let's see. So Alice has an arbitrary qubit and Alice wants to send this arbitrary qubit to Bob. Okay, you can tell me that, okay, I put this arbitrary qubit in a box and then I courier it or I post it and Bob will get it because Bob will open and get the quantum state. Okay, you have to somehow send it in such a way that it is not destroyed. But this is always true in our also for classical, say I want to send a letter to my friend, then I want to put the letter in such a way that it is not destroyed, or it is not destroyed, say in rain or something. So I have to put this quantum state in an envelope in such a way that Bob gets the state as it is. But this sending physically, that is by using courier or post, is not, suppose it is not allowed. I want to do by using like a bit or something. So how Alice will do? Now you can tell that if to send this arbitrary qubit, if Alice and Bob prepares or build a bridge between them, a quantum bridge between them, then Alice can successfully send this arbitrary qubit to Bob. Now this quantum bridge means a quantum state that Alice and Bob can share. Now I will talk about this quantum state later on. Let's just tell you the protocol first. So what Alice will do, Alice will perform some measurement, then sends the measurement outcome via phone call, for example. So Alice will send 2 bits of classical communication to Bob, and finally Bob will get the state that Alice wanted to send. So here the resource that you require is a bridge between Alice and Bob plus 2 bits of classical communication, and these 2 resources will help Alice to send an arbitrary qubit to Bob. Here you remember, in a classical device, that means if I want to send an arbitrary qubit to Bob, then I need infinite number of bits. So I need infinite amount of classical communication. Here I need a bridge between Alice and Bob and only 2 bits of classical communication. So I see by using quantum mechanics, you can reduce or infinite resource reduction is possible. So this is the quantum teleportation protocol. It was discovered by these 6 scientists in 1993, showing the importance of building quantum communication technology. Now, the way I was telling, this is like a magic, but it's not a magic. The basic ingredient that we require to build communication device in this scenario, or in this, if we want to perform quantum teleportation, is quantum mechanics. Or in other words, the properties of bridge help us to fulfill the task. And this properties of bridge is called entanglement. And this name was coined long back around 1935 by Schrödinger. And this entanglement actually is a property of the bridge that Alice and Bob has built. And that helped us to transfer this arbitrary qubit from Alice to Bob. Now this theory was developed very nicely over last 30 years or so. We have also written a chapter of a book and a review article where we showed, we discussed several properties. And these are the 3 pioneer scientists from Poland. They also have written a very nice review article on theory of entanglement. Now, just very briefly tell you what is entanglement. Again, I'm talking about a scenario where Alice and Bob are situated in 2 distant locations. Now, suppose I consider this mathematical expression that we do every day in school. So suppose this x, the pink, they are all complex numbers. And this x, the pink ones are with Alice, and the capital letter and the black ones are with Bob. And you see that you can write this variable in this way, the factored form. And these are the unentangled states or the useless states. That means if the bridge is unentangled, then the task that I have described is not possible to perform successfully. Now, here I have written a much more complicated mathematical expression. Again, the pink ones are with Alice and the black ones are with Bob. You see, again, you can write this in a factored form. This is also an unentangled state. Whenever Alice's part can be factored from the Bob's part, that states quantum mechanically called the unentangled state or the useless states. That means they are not useful for the communication or many other quantum technology that we want to build. On the other hand, you see, if I consider this mathematical expression, this is not possible to factor. So this you cannot factor, and these states are called the entangled states. Now, instead of this complex variable that I'm talking, if we use that in vector, then that lead to a non-factorizable vectors, and that lead to an entangled states. Now, if I want to talk about entanglement in a more from the experimental point of view, I can tell the following. So useless states are those states that Alice and Bob will not be able to prepare when they are situated in far apart location. That means unentangled states are those states which Alice and Bob will be able to prepare when they are situated in two distant locations. So they will be able to prepare these states even when they are in Bangalore and Allahabad. On the other hand, entangled states are those states that Alice and Bob will not be able to prepare when they are situated in far apart location. Now you can ask me the question, then how will Alice and Bob will be able to prepare this, build the bridge that you were talking about in this quantum teleportation protocol? Yes, this is possible. For example, you can think there is a source, third party. Suppose Alice is in Bangalore and Bob is in Allahabad. Then there can be a source which is situated in Mangalore. Now, source will prepare these states, this entangled state, then source send one particle to Bangalore, another particle to Allahabad, so that finally Alice and Bob share an entangled state. So in this way, experimentally, this entangled state can be shared, or this bridge can be built. Now, we probably, as we know that in communication, at least in classical world, many people are connected by this communication network. So we finally want to build that kind of communication network. So we want to share this kind of entangled state between several parties over large distance. That's a real challenge. And actually I work on this aspect. So I work how to build a communication network in any, if we really want to, where many people will be connected via quantum states, via quantum entangled states. And we have done several works over the years in this direction. Now again, the question is whether this is just a theory that I'm talking about. It's not, because communication devices are very, actually it got a lot of success over the years by using several quantum mechanical systems. And experimentally from 1997 onwards, there are a lot of experiments in these directions where the several communication devices have been built. So for example, photon, we know that they are these particles or wave, whatever you want to tell. This can be described by quantum mechanics. And if we want to talk about certain property of photon, say for example, polarization is one of the property that photon has. If we use that, one can prepare this bridge, that is, one can prepare this entangled state, and hence they can actually implement the quantum teleportation protocol that I have described. For example, in few years back, quantum teleportation protocol was demonstrated between two islands which are nearby. So this is Spain and this is the Africa. There are two islands called La Palma and Tenerife, and they built, this is 143 kilometers away, and they built a bridge between that quantum bridge that I have talked about, and they performed quantum teleportations over this distance. So in some sense, just to tell you that they can perform quantum teleportation between, say, Varanasi and Allahabad, but in 2016, it was not possible to perform teleportation between Bangalore and Hyderabad, because it's around 500 kilometers away. But recently it was shown that a Chinese group has demonstrated the quantum communication protocols between two cities which are 1200 kilometers away. This is J.W. Pan who led this experiment, and this actually tells us that there can be a teleportation protocol, for example, between Ahmedabad and Hyderabad, between Bangalore and Hyderabad, and so on. So in 2020, it becomes a reality that in a long distance, quantum teleportation protocols can be implemented. There are other physical systems where also this quantum communication devices can be built. One is ion trap. There are ultra-cold atoms in optical lattice where these lattices are created by laser. There are nuclear magnetic resonance, some molecules which actually can display quantum property, and you can implement quantum protocols there. There are semiconductor devices, and probably one of the promising one nowadays is the superconducting qubits, where the currents, which way the currents are going, that actually help us to build the qubit or the quantum computer or quantum communication devices. So finding a good physical, means quantum mechanical systems where quantum computers can be built, or finding a good quantum mechanical system where quantum communications can be implemented, are an important question. And as I have told you that to the success of this communication protocol occurs due to the presence of the bridge between Alice and Bob. That means this bridge is, as I said, is an entangled state between Alice and Bob. So finding useful quantum systems where entangled states can be created are an important question. And I work in these directions with my students in recent times, and we have done some progress in this direction. We have also written 2 review papers where we address these questions. Now I think I have some time where I can very shortly talk about secure communication. This means that we talk about a quantum version of the secure communication. So what is secure communications? I want to, again, Alice want to transfer something Bob, but there is a eavesdropper in between. That means there is a third party who wants to gather information that Alice is sending to Bob as much as possible. So eavesdropper aim is to maximize the information or to obtain the information maximally that Alice is sending to Bob. So up to now, this quantum state transfer or the protocols that I have described, there is no third party. But in communication, secure communication protocol, there is a third party who wants to gather the information about what Alice is sending to Bob. Now, secure communication probably is very useful. And again, this COVID-19 situation, we realize that because we use internet banking to transfer money to many people, to friends, relatives, we use all the marketing, everything, buying, everything we have done via internet and via Amazon, for example, where we either use internet banking or we use debit card. But this secure communication are also useful for national security. For example, in war, in ancient time, when the soldiers are at border and the commander is in some office, and commander wants to send some information to their soldier, of course they want to send it in such a way that the opponent do not get the information. So they have to send it securely. We don't want war, but this is the way actually the national security has been developed. For example, World War II, there are several secure machines were developed, secure communication protocol were developed, which helped them to carry informations to inform soldiers. Now, all this internet banking to national security, all are kind of, I mean, we believe and we are, I mean, from our daily experience, we know that they are all very secure. Now, so why we want to build the quantum version of it? Now, the point that I want to make is the following. the classical crypto system, that means this internet banking or something, their security is based on the belief that some mathematical problems cannot be solved in classical computer in a reasonable time. For example, the prime factorization problem that I have described in the beginning of my talk, I have shown you that it cannot be solved by using even a powerful classical computer. Now, all these classical crypto systems that we are using, they are old, their security are based on this belief that these prime factorization problems cannot be solved by using classical computer. And that's why we get the security. Now, the twist of this whole scenario is the following, that as I have also told you, that these mathematical problems can be solved by using quantum mechanics. So if someone built a quantum computer, then all the protocols, all this internet banking to national security, all will be unsafe. So quantum mechanics makes all current crypto system insecure. So what to do? Again, quantum mechanics can develop certain protocol and can give us some remedy. So in some sense, we can build quantum cryptography where the security will be based on the validity of quantum mechanics, which I think now we believe that the quantum mechanics is valid. So, and the important point is this quantum crypto system that we can build, that means a crypto system based on quantum mechanics that we can build will be secure even when there is a quantum computer. So if we now replace internet banking, national security, everything is based on quantum mechanics, then they will be secure even when someone has a quantum computer. There are two important protocols that was proposed, one in 1984, another is 1991. In all these protocols, the key that you require, that I have told you that in secure communication, you usually have a lock and you have a key. Here the key is by using quantum mechanics. In other words, you randomly generate quantum states and you share between, and these random states are shared between sender and the receiver. And if the eavesdropper wants to intercept the key, or if eavesdropper wants to gather information about the key, then the laws of quantum mechanics ensures that eavesdropper cannot do this without disturbing it. And this was also proved by these two people, that quantum cryptography will be secure even when there is a eavesdropper in up to certain level, because the reason is, the main reason is the following, that if you disturb quantum states, then it can always be detected. And this was proven by these two people. And this was the three people who actually developed initially the quantum key distribution protocol. This is Arthur Eckert, this is Brashad, and this is Charles Bennett. Now again, the question is whether it is only a theory. It's not. Actually, quantum cryptographic systems have also been realized even in a realistic scenario. For example, there was a football World Cup in South Africa where they used quantum cryptography to securely sending data between between stadium and the some offsite joint operation center. Even in the Geneva election, they use quantum cryptographic system to securely transfer information. And in Geneva and these places, the people who have done that, led by Nicolas Giza, and in Switzerland. Now, in this respect also we have found that there is a quantum key distribution protocol, there is a complementary relations, we give the bound on secret key rate. We also work on some concept called monogamy of quantum correlation, monogamy of entanglement. And that actually has a very that actually helps to build the security of cryptography. Recently, we have shown some helped us to give some security aspects when there is a crypto system between several people. Okay, so I come to the end of my talk where I think you are convinced that we are leading or we are heading towards new technologies. So quantum mechanics can revolutionize computation and communication capabilities with and without security. So quantum cryptography is a reality. It can be found in even in 2018 or even before. I think they can be built. We are expecting to have quantum internet. That means quantum communication network, which connects several senders and receivers. You can communicate to any parties. And finally, probably we want to build a quantum computer which can outperform classical computers' capabilities. So I just want to show that this is the QIC group at Harishchandra Research Institute. There are some past members. There are some members which are now actually faculties in several Indian institutes. So currently we have 15 PhD students, 5 postdocs and 3 faculty members, and several visiting students. So any of the students who are interested to learn more about quantum computation, quantum technologies, please write to me, please email me, and I will be very happy if I get an opportunity to visit someday to these schools. So thank you very much for your attention.
Thanks, ma'am. Now we will have some questions, ma'am. Satilingam?
Should I stop sharing or?
Yeah, okay, ma'am. You can please stop sharing.
Okay.
Madam, good afternoon, madam.
Yes.
Madam, it is a very difficult topic and you explained in a easy way to understand. And madam, this one, but the few experts are telling that even the family photos, our data should not be kept even in a WhatsApp, this and all. In what way the quantum computer, it will can save us in future? It will be a future. That is the first one. The second one, is it in communication? You spoke, madam, in the communication. Is it possible to use the elementary particles for better quality? This is my second question, madam.
Yeah. So the first question I answered that yes, it's true that if you use classical. So I said that the classical cryptography is secure in a sense that if there is no quantum computer, it cannot be hacked. But as you correctly pointed out, that the WhatsApp or in other internet email, many times we see hacking. And this is because that, to build really a long key, which can give us a security, is very costly and very expensive. So usually the key that we use to secure our systems are usually not that big, which makes all the crypto system to be secure. And that is why we still, even without the presence of quantum computer, this can be hacked. But as long as the key is big, you do not repeat the key and so on, there are some conditions, then the classical crypto system that we are using is secure. Now the question is that suppose I make a very long key that I have talked, like 100-digit key or something, then really the crypto systems that we are using will be secure. But the 100-digit key generations will be very difficult, very expensive. Now, if we have a quantum computer, even the 100-digit key is not enough, because in principle, it can be broken by using quantum computer. So in that sense, so suppose as you know, that when we write down the password, usually it gives you the suggestion that your password will be 8-digit, has some special character, has some number, and so on. Now, these are the things that makes this key generation, or this makes the key more secure. Now, the point is that here you want to, but whatever security or whatever way you complicate your password, if really one has a quantum computer, you can actually break the key. So that's the principle wise it can be broken. So this is the first answer of your question. Now the second question was the quantum, the particle that you were talking. So here I am talking about a microscopic particle. So it will be, the quantum computer will be built by using microscopic particle. You can think the spin of an electron or something. That way we will build.
Okay, thank you, madam.
Thank you.
Yeah, any other queries? Nagbuster?
Ma'am,
Yes.
I have another doubt. You are talking of the quantum computing technology. Ultimately, the gadgets are to work on the electricity. Will there be any revolution in the way the electrical lines which will support these gadgets also in the future if we are switching over from the classical to quantum computing?
Okay, so the point is that usually you okay, so I think that what the your very justified question, but the point that if you want to build a quantum computer, then you use laser and other quantum particles that I was talking, electrons, photons, ions, superconducting devices, and so on. So how and they can build a small scale computer that I have shown. Whether we really want to build a 1,000 qubit computer and actually can revolutionize the entire technological system, whether we really need also the electrical more power or electrical revolutions, we still don't know. But up to now, whatever systems we can, whatever quantum experiments that we can do in our laboratory using only this thing, and also the data that we simulate in quantum computer or quantum thing, you can also, I mean, there can be a, you know, the quantum computer will also have a capability to do all the gates that you can do even in classical computers. So in some sense, it has been technically shown, or it has been shown theoretically, that you don't need quantum computer as well as classical computer. All the things that you can do in our desktop laptop, you can also be able to do quantum computer. But we have to build it, which I think is far, and also the more or less the timeline that they put in European Union, US, China, all these 15, 20 years. And as you know, that probably around 1970s, 60s, how big was our computer,
Yes,
and now
yes.
how small is our iPad, and even the mobile, the data that you can store is huge. So I think that this development will come. We will understand that how the things will be changing. Whether
Thank
we
you.
need a different kind of technology to support quantum computer or not, we still don't know.
Thank you, ma'am.
Madam, one more question, madam.
Yes.
Madam, one student question from my student. To develop research in quantum computers, so which course he has to choose, and what are the best colleges to study to continue the researches and so?
Yeah. Okay, so now, you know, there are a lot of effort from DST and other Indian government. So there are there is an effort to build quantum technology group and so on. So probably you have heard that there is 8,000 crore has been invested for quantum technology and so on. So this is a government has declared, and Department of Science and Technology are now trying to make this framework. So there will be a lot of development in coming years, in next 5 years. So there will be many institutes where the training program will start and so on. But I think that if you do bachelor's in any science stream like physics, mathematics, even computer science, electronics, you can always do this quantum technology course. So we also need electronics. We also need different, for experimentalists, there are several other expertise are required. From theoretical perspective, yes, if you are a physics student, of course you can do both theory and experiment. And there are also mathematical aspects of this quantum technology mission. So that part also you can learn if you have a mathematics in your course. So I think these basic subjects can be learned in all the colleges in India, right? And so any colleges are good. And quantum computation, especially the subject can be taught in master's level and in PhD level in some institute. For example, Harish Chandra Research Institute, we have quantum information and computation 2 courses. One is QI, quantum information and computation 1, and 2, which is a bit advanced level. So MSc students can take these courses. Even we have a summer school, and even during bachelor time, you can come in our institute and in many institutes in India as a summer students and can learn this subject. So there are many opportunities, and I believe that in next 5 years, there are more opportunities coming in India. And in abroad already there are several institutes where several places this kind of training is going on. But in India, I think there are also many places where you can learn. And so I think that if you just go to a normal college where you learn basic science initially, quantum mechanics is one of the area that you usually learn, and that will be enough. Basic quantum mechanics will be enough to learn of quantum technologies.
Thank you, madam. Really, we will motivate our children. Thank you.
Yeah. Yeah, Srinivasan, sir.
Yeah.
Yeah, any other queries from
No.
participants?
Yeah,
okay. No? So I'll ask Prahlad to propose vote of thanks. Yeah, Prahlad, sir.
Good evening, ma'am. Ma'am, like your talk was the most relevant topic, I feel. Because normally a layman is always on his tenterhooks when he is dealing with internet, particularly when he is dealing with his financial issues like internet banking, purchasing, and all those things. For a layman, really, you have opened a big ocean and a ray of hope for the future. Otherwise, particularly people like us and our children, most of them are in rural areas, still fond of using internet and all those things. I'm very sure without your talk today, they should have been still in the tension. Neither they could completely quit using internet, nor they should have confidently used it. Probably this quantum mechanics, particularly the way you have explained the classical quantum mechanics and the advanced version of quantum mechanics, really it has given a hope. More than the hope, they are confident now. If not today, at least in near future, their accounts, their dealings would be secured. And particularly what you said that with this quantum computing, eavesdroppers could be detected. That's more than enough, because our security system, our police personnel, also very strong. But people like you, with your researchers, when you are providing such a great technology to find out eavesdroppers, I think that's a big hope for the future world. A layman like me, really so happy, so happy. Your talk was really so refreshing for us. And madam, like on behalf of Navodaya Vidyalaya Samiti, I'm I'm conveying my candid gratitude because you have offered open invitation for our students who are interested to join this Harishchandra Research Institute for learning quantum mechanics, particularly in communication, for your generous offer and generous invitation on behalf of entire Navodaya Vidyalaya Samiti. I'm really thankful to you, ma'am, and hope your patronage, your association with schools like Navodaya Vidyalaya really be required. Hope in the days to come, you would be giving more and more lectures, and we would be very happy to have such wonderful topics from very scholarly people like you, man. At the same time, I would like to convey my candid gratitudes to JNV Chitradurga, JNV North Sikkim, and JNV Mangalore for their continuous cooperation to have these talks of eminent persons like Dr. Aditi Sen and other people. And I'm also very much thankful for Navodaya Vidyalaya Samiti Hyderabad region and Navodaya Vidyalaya Samiti headquarters Noida for constant support. Ma'am, certainly it's not an exaggeration. It's really a big ocean of knowledge you have opened up. Otherwise, really, we should have been in darkness. So thank you very much, ma'am, once again for your wonderful talk.
Thank you. And I hope that I will come sometime to schools when things are easing up.
Sure, madam, sure. So thank you very much, madam. Thank you for our. Okay, madam.
Okay, so I stop. I leave.
Thank you very much.
Thank you. Bye-bye.